Okay, you have thought about your socio-hydrological problem? Who has thought about a problem? All of you? More or less. Okay. Before we go into the individual problems, I would like to explain the 7 steps of how to frame a socio-hydrological problem. 7 steps. 7 is a good number, right? 7 dwarfs and 7, you know, in fairy tales, 7 is a good magic number. So 7 steps, and I will explain them first, and then we will take an hour, and then we'll have maybe a flood example, and a drought or irrigation example. There could be, I'm not sure whether navigation is a problem in Brazil. I'm currently running a project with the German Water Authority. I'm running a project with the German Water Authority where I'm doing exactly the same thing with the water managers in Germany. So we went through the same exercise and we came up with 7 or 8 examples. One was navigation on the waterways in Germany. The other example was tourism, water and tourism. Then there was, of course, water supply, and there was floods and irrigation. There was also cooling water for thermal power plants. When you have power plants that you heat with oil or gas or coal, you need to cool it, which has effect on the water. Right? So we had a couple of examples, and we can do the same thing here for your problems, and then they should have a spectrum, right? Water quality, of course, also. Okay, so I'll start with the 7 steps. And can you bring up the table? Yes. Please, the paper. Okay, and can you make it a little bigger and remove the zoom in a little bit? And remove the border on the right-hand side, and so we can really maximize the screen because the font is a little small. Okay, what is the first step? Very good. Okay, maybe a couple of remarks about modeling in general. There are 2 ways of approaching mathematical modeling in general and also in hydrology. One is called the upward approach, and the other is called the downward approach. Have you anybody heard of that upward and downward approach? Yes or no? Okay. Can you comment on it?
Yes, a little bit. The first one, the come down, you start with the water and ends with society, and the other one you starts with society and ends with the water, something like that.
Yes, this is one way of looking at it. Other comments, other perspectives? So it's very good. Other? Well, the other perspective is the following. You have a complex system, and the upward approach consists of starting with the individual components, combining starting and modeling them, representing them by equations, then combining all the components to get the entire system's response. Okay, for you're water scientists, right, mainly. A rainfall runoff model, you know what that is. It rains, part of the water infiltrates, some of the water evaporates, some of it runs off on the surface, right, the rainfall runoff model. There are 2 ways of approaching that. The upward approach is that you start with Richard's equation for infiltration. It's Darcy's law with mass balance. You use shallow water equation for surface water flow. You use the Darcy equation, the saturated flow. And then you combine everything. You do this in small pixels of a square meter. You represent each of these processes in a small pixel, and then you say, well, the catchment, 100 square kilometers, it's just 1,000,000 pixels. You combine them, and that's it. That's called the upward approach. You start with a small scale, individual descriptions, and combine them in a way you think you should combine them. Not necessarily in the way that it's best, but just think, because you have no guidance from data, from reality, how to combine them. Just think you combine them the way it's best. The upward approach. The downward approach is the opposite. You look at the response of the catchment. It rains, and the water level increases in the stream, of course, because the water runs off. Then you look at the shape of the hydrograph. You do this for short and long storms, for big and small storms, and then you infer back what is happening within the system. This is the downward approach. You don't start from the small pieces, you start from the big picture, and then scale down to the individuals. When there is an election, one party gets 60%, and the other party gets 40%. That's the result. You start from that and ask, why did the Conservative Party get 60%, right? And then this is the starting point. And then you ask people, and you scale down to what individuals people do. This is the downward approach. Upward approach is, I'll make an interview with you, and with you, like a poll, and I combine everything, and then I predict the election result. There's two possible avenues of approaching this modeling problem, okay? Here, we usually start with the downward approach. We can also start with the upward approach, but this is for the downward approach. We look at the entire system behavior, and that's why step one, we look at the phenomenon that we want to represent, we want to model. A socio-hydrological phenomenon. What is a socio-hydrological phenomenon? We should now have 40 phenomena, because you thought of 40 examples. I'll give you an illustration, and then I'd like to hear your perspective, your examples. A phenomenon is called the levee effect in flood management. The levee effect is the following. There's a river, and the river tends to flood, inundate the floodplains. Now, to reduce the flood risk, so people do not get inundated all the time, the municipality builds a levee to protect the floodplains and the buildings, the infrastructure from the flooding. And because the people now feel safe, they move into the floodplain. So the population density and the value of the infrastructure on the floodplains increases. And of course, the levees don't have an infinite height. They are sometimes overtopped. So sometimes, rarely, the floodplains are flooded. And now there's more value, more assets in the floodplain, which increases the flood risk. The flood risk is the expected damage per year, right? That's called the flood risk. So you have a flood problem. You build a dam to reduce the flood risk, but because of the coupling of people and water, you increase the flood risk. Why? Why? Why is that happening? That's a phenomenon. Okay, that's an interesting phenomenon. It's not obvious. We can use a sociological model to explain this phenomenon. Okay? Now I would like to hear your phenomena. Okay? Who would like to make a start? Okay, two starts. You start here and then you're next. Yes, start your name and then...
Okay, I'm Cesar, and I'm gonna talk about floods in Belém. I'm from Belém, is Amazon region. So there we have a lot of problem with flood, especially at this time because the river its level is so high. Then the river invades the city through the channels. So we have the natural behavior of the river, and we have pollution there because people throw trash on the street, on the channel, and we have politics. The only thing politics do, they clean the channel every year, only this. But it's not enough. It's not enough because people still throwing trash, and the river is its level always grows, and so it's a problem that happens every year.
And one wonders, why don't politicians manage to clear away all the pollution, or why don't people stop to pollute? Why? That's a sociological question, right? Very good. I will write down this, and I call it flood pollution. Flood pollution, just, and your name is spelled with A-E, Caesar?
Yes.
C.
E-S-A-R.
Like that?
Yes.
Flood pollution, and where is it? Is it the Amazon? Or in the region, right? Amazon. So we have a phenomenon, and we have also location, because we want to be real. Okay. Please.
Hi, my name is Felipe. Well, my problem concerns the metropolitan region of São Paulo. And basically, the water supply comes from a reservoir called Cantareira, which supplies dozens of cities, not only São Paulo, but cities around. And it suffered a water crisis in from 2013 to 2015. And basically, I'm interested in understanding how people demand such water. How people consume water, you know. Because before the crisis, there was enough water for everyone, and people was consuming a lot of water. But during the crisis, during the shortage, people decreased the consumption. And you know that today, almost 4 years later, people are consuming more water than before the crisis. So there are some social variables included in this problem, such as memory, such as media information, and all these things, you know.
Very good example. So how do you spell your name? Philip? Yeah, Philip can spell in different ways. F-E. Say it again. F-E. F-E. L-I. Double P? No, only one. Like that? Not correct?
I can see. I'll get closer. Felipe, no, only one L-N-E. Yes, there
Thank you. Sao Paulo water supply.
Yes.
Okay, very good. We'll not have 50 examples. Maybe we can have an example from the other two campuses. Would this be possible? How do we? Can you just maybe repeat the question for clarity? It's the phenomena, right? Phenomenon. Ah, 7 minutes. Okay, seven things. Okay, we can do one more here. So they
The Amazon, so we have one example of Amazon, another for Southeast Brazil, because this region is called Southeast Brazil. Peru, we have an example from Peru.
Peru. Very good.
I talk about watershed Vilcanota. Eu posso falar, mas meu como se chama? Meu. Você fala em espanhol e eu traduzo. Sim. Desculpa, mas não posso falar, não consigo falar muito. Eu estou misturando na inglês, português, ainda tenho problemas, então vou falar em espanhol. Sim, ele vai traduzir. Sí. Disculpa. Allí tenemos el problema en la cuenca, principalmente en la parte alta, media, baja, tiene mucha contaminación. Ninguna institución realiza, ¿cómo se llama? Han divorciado la infraestructura, la ciencia y la parte social. Entonces, como existe el divorcio, no existe una organización, algo que les pueda unir, razón por la cual que tenemos bastante erosión, bastante sedimentación, bastante inundación, problemas en la parte baja. Porque considero particularmente que eso hace que se tiene que tener conocimiento de las personas. Yo veo aquí en Brasil, al menos, las personas conocen, tienen conciencia ambiental, ¿no? De protección del agua. Entonces, allí en Perú, ninguna persona tiene esa conciencia de proteger el agua. Entonces, razón por la cual considero que eso se debe de articular.
¿Qué es el fenómeno? ¿Cuál es el fenómeno?
Erosión, sedimentación, principalmente.
Okay. Thank you.
You understand?
Yeah, yeah.
Okay.
Just one, Spanish is easier than Portuguese. So, your name was? Jose. Erosion. Sedimentation is also upstream, downstream, understood, right? It's an upstream, down, which is an interesting erosion, sedimentation, upstream, downstream, which makes for interesting hydrological problems because people usually defend their own interests, right? We all usually, we're quite egoistic usually. We represent our own interests. But if it's upstream, downstream neighbors, the interests are competing, right? There's no solution where everybody is happy. There's often compromises. So upstream, downstream, and the river basin, I didn't get the name. The name of the, el nombre de la cuenca?
Vilcanota.
How do you spell that? Peru. Sorry. Okay, maybe we have examples from the other campuses. Still discussing. Yes. One more here.
Northeast Brazil? Yes.
Northeast. Would be Belém, or where would that be?
So, hi, my name is Bruno, and I'm going to talk about the city where I come from, my hometown. Yes. It's called Rio Real, and it's a city that produces orange. But there is a problem that they use groundwater, but the water table is going down, and then every year they have to dig a bit more. Every year they have to dig a bit more, but it's not working anymore. And the problem is, if with the economy of the city is only orange and the city council, that is the only economy we have. Then if the production of orange decreases, the economy goes down, and the population doesn't have another option to make money, to survive. Because, for example, sometimes if we have a small quantity, small production, for example, we decrease the offers of jobs, because there is a lot of people working on the farms. Then we decrease, less jobs, less money circulating in the city. Then there is this problem. And we have tried to start digging deeper to confined aquifers, but it's not economically viable. Then that's our problem.
Thank you very much. I think it's a very clear problem. Can you give me your name? Bruno. It's easy. So this would be horticulture, or oranges, right? Oranges and groundwater depletion. And the region would be?
It's northeast Brazil. Northeast Brazil.
Okay, now the other campuses, are you ready? They cannot hear me, right? See.
They say they are thinking, and I said, no, you should have one example for each one of you.
Cada uno, okay.
Okay, Francine from Federal University of Campina Grande.
Okay. Now let's see. Let's speak her or him. Yes, we need the microphone.
Hi. Can you hear us?
Yes.
Felipe, yes? Okay. Hi. The problem I'm studying is about the urban river, and I'm looking for the land use changes over the past 20 years, because a lot of habitational settlements were built over there, or built, and I'm studying how the land use change affects the runoff and how it impacts the river.
Okay.
This problem is located in Aracaju. It's the capital of the Sergipe state, and it's a coastal city. It's a coastal city, and the river is the Rio Poxinho River.
Okay. What I would like to have is not only a question, but also a hypothesis of what is happening. Right? You just said, what is happening? What's the effect? But also I would like to hear the answer to that, what you think is the answer, or what you observes. Can you type this? A phenomenon, just do the full narrative. So we build a narrative, a story. This is what social scientists are very good. They make a story, which has the nice feature that you can represent complexities, nuances, which in equation you cannot. Right? We start with a narrative, with a story. What's happening? Once upon a time. Okay. Ah. No. Okay. Can somebody help me with her name?
Can you ask again, please?
Could you ask your question again?
I'd like to have a hypothesis of what the effect of the land use change is on the erosion. Where's the socio-hydrological phenomenon? Where do people come in and what's happening? You were stating the question, but I would like to have the answer to that, to see what is their people-water interactions. So people are clearing the land, then there's more erosion, pollutes the river. So where are the dynamics, the interactions? Feedbacks between people and water.
Qual a hipótese
do efeito de erosão?
Perhaps
Que atraiu a crescimento da cidade, agora é o rio que eles não querem mais. É isso? É o rio que atraiu a cidade ali para a costa, agora é o rio que eles querem desviar, relevar, inclusive construir costa para ele.
land use,
É isso?
cultural aspects, like
land use.
norms
Na
and
verdade,
values are important because they land use depend from that. So the cultural heritage.
Okay. Yes, understand. Okay, let's wait and then, yeah, very good. Okay. That's a good answer.
In several regions, we have several or different cultural heritage. So Northeast Brazil with different climate and weather, and also South or Southeast Brazil or
can
even
you
Amazon.
listen to us?
Okay.
Very good.
Felipe, can you hear me?
Yes.
Okay, so her interest is about, because now the river is inside the city and the people don't want it anymore because of the population growth and the modifications in the urban system. And what else?
What I think that is the problem. It's because the situation now, in spite of the city is growing close to the river, this interaction is not planned. So the proximity of the population to the river is not planned, and this causes negative impacts in the river, in the quality, in the river quality. So this is the problem. The city grows close to the river, but the impacts are negative.
Okay. Thank you. What is your name? Huh.
My name is Shalana.
I'm lost. Who can help me? Ah, you too.
H-A-L-A-N-A.
I'm also from Rio Real, as the
Shalana, and we had, help me with just summarizing that, because you listened all. It was about urbanization, I think, and urban planning, and the water effect was it sediments? Sediments, or what was it? Urbanization and sediments. Siltation of the river or of a reservoir? River siltation, very good. So it's sediments, it's urbanization. Can we in the meantime ask the other group? Thank you very much, Shalana. Thank you, appreciate that. Very good example. And can we now move to the other group, bitte? Urbanization, river siltation, and where is it? J? Thank you. Okay, the other group? We probably have also time for one more example here, right? You have one. Very good.
I am Maria Clara, and my problem is here in. Oh.
I am Maria Clara, and my problem is here.
Okay. Hi everyone, my name is Alfredo. I'm not a student. We have here 20 students and maybe 20 problems, but at the moment, no one wants to explain your own problem. Okay, but talking with the students here, we could identify two cases, I think, can illustrate some of the problems we have in Pernambuco State. The first one is related to the extraction of the sand from the bottom river. This kind of problem happens in the rivers that we can call ephemeral rivers, because there are water only during the rainy season. In these cases, there are extractions of the
We do you later.
He's talking about a non-perennial river, but then it stopped.
Not yet. Okay, let's do the flash flood forecasting.
Yeah. The problem is here in São Carlos. We often suffer with urban floods, and there is a commercial area in the floodplain, and the shopkeepers don't want to move from there, even the flood happening.
I know. Are you listening now? Can you hear me?
Yes.
And did you hear the first case? No? Okay. I will repeat. Okay. We selected two cases. The first case is related to the rivers that we can call ephemeral rivers, that there are water flowing only in the rainy season. In these areas, there are extraction of the sand. You can understand that the sand is the environment to keep the water available to the population. Some companies extract sand of the bottom of the river, and this causes a problem to maintain, to keep the water in the groundwater for the population. So it's necessary to intervene, to control, to manage the extraction and the water used to supply the population. The other example is the water used in small reservoirs during the drought period. It's necessary to find the water location for given supply and for irrigation. So there are many cases in small reservoirs or medium reservoirs between the water supply for human and water for irrigation. Here we have some students that work in the water sanitation company, and I think they have some examples similar to this to work in the next step. I hope you could listen this example.
I think the first one is related to non-perennial rivers and non-perennial ephemeral rivers. And the thing, rivers, yeah. And the thing is that some companies, local companies, they extract the sand from the bottom, from the riverbed. They extract the sand, the sand material. And this causes non-equilibrium within the system, relates to infiltration of the water, and because we have only the few months of the year with rain and with runoff, and of course with infiltration. And if we extract sand, the system is somehow perturbated, changing. Yeah.
Okay. So can we get the name of the region?
Pernambuco is the name of the state. He didn't point an exact location. Alfredo.
Zara, could you repeat that? I missed that part. Ela falou sobre riverbed.
Sand extraction. Ele escuta? Ele me escuta? Não. Sand extraction from the riverbed. Is that?
Okay.
And he gave a second example related to the challenge of allocating water for multiple uses, for water supply and for irrigation. For
These are all questions, not phenomena.
yes. Alfredo, did you hear him? He's saying that these are the questions. He wants the phenomena.
Yeah.
These are the questions. He wants the phenomena.
Okay.
Maybe we stop here and move on.
Come back.
In terms of non-perennial rivers, ephemeral rivers, this is very important because we have poor people, very vulnerable people living in the countryside of northeast Brazil, spreading in the countryside, living from these small dams. They build up waiting for the rains. So, and very dependable from the rivers. When the rivers have waters, the community has the harvesting process on, switched on. And the groundwater for alluvial deposits. But when the rains in a year didn't come, these people sometimes need to migrate somewhere else, big cities or even other cities.
Sand extraction related to that?
So,
Sand extraction?
not necessarily sand extraction.
It's a different problem.
No, this is a different problem because it's ephemeral rivers that sometimes they are flooded because the big rains come and all the community and economy works if the rain is inside.
Yeah, but I think the sand extraction relates to the infiltration conditions because you have a not infiltration condition because we have these alluvial deposits. We have basically sand and then clay layers, and so it affects the infiltration when you remove the sand, the natural conditions.
Lots of things to be discussed about the phenomena. What is he saying?
Okay. Impact the groundwater availability is the infiltration because they depend on groundwater.
Okay. So it's sand extraction from the riverbed and groundwater, yeah. Okay. Then maybe a final example. Sorry for no interruption now.
Okay.
No interruption now. Let's hear it out.
Okay. So here in São Carlos, we often suffer with urban floods due to growing urbanization without management. And the commercial area of the city is in the floodplain. And the shopkeepers don't want to move from there because even due to the economical losses, because they feel that they belong there, and if they move to another place, they are afraid to lose the shoppers, and they don't want to have memory about the floods, so they don't allow the civil defense to put marks of the floods because they think it will put away the shoppers. So it's
very good example. Can you give me your name?
Maria Clara.
Maria. Thank you. So it's Maria. Urban flooding. Awareness of shopkeepers. This is São Carlos. And here we had also groundwater. Okay, I suggest we stop here. I think the story to be learned for you to take home is we start with a narrative, with a story that it has some causality. One thing leads to another. Like in a fairy tale, fairy tale starts with a princess and then the witch comes and one thing leads to another. Same thing here. You extract the gravel and then the groundwater infiltration drops and so forth. One thing leads to another. It's a narrative. This is our starting point. At this point, I need to point out that there are two kinds of modeling. There are two ways of building socio-hydrological models. The first kind of model represents reality. There's a narrative, and you implement this in the model and with these 7 steps, And then the model simulates the reality. Ideally, you have data points of the awareness of the shopkeepers or the dredging of the riverbed. You point them against the line is the simulation, the points is the data, and you say, my model represents the data, and I believe the mechanisms in the model also represents reality well. Then I can do sensitivity analysis and look at the components and make predictions, etc. This is the first kind of model. The second kind of model tries to optimize the behavior. This is what economists all the time do. They have very similar models, not about water so much, but about environment in general. But then they're not interested in representing what happened in the past, but they are framing their problem and then say, I define an objective function. An objective function is the target. And what is the target for economists? Always money. Economy is the science, well, of how making money with scarce resources, right? But there's an objective function which is about money, right? And they optimize it. How can I optimize my income or optimize some number related to money, right? And then they get a parameter set and say, you need to manage the system this way or this way, manage your business, your company usually, or your country if it's macroeconomics. There's microeconomics, micro, small, which is about individual businesses, companies. And there's macroeconomy, which is about countries, nations, about exchange rates of the money and national economies. Macroeconomics, but the idea is the same. You provide decision support, how people should manage their country or their business. These are the two kinds of models. And this week, I would also only like to talk about the first kind. If you want, we can also discuss the other kind, the optimization. This optimization is more for management. The first kind is more about understanding, but understanding also can help management, of course, right? So we've started with these narratives. That's our starting point. And then that's step one. And can you bring up the table, please? So we can read it. Very good. If you magnify it, please. So, step one, phenomenon, domain, scale. Specifies the phenomenon. For example, rainfall, runoff, transformation, scaling of floods. Okay, we did this first step. The first 2 lines we've done already. We have another 100 lines to go. Let's do the second step. Specify the control volume. We will not do this for all of the examples, but I would like you to understand what it means. You're engineers, you know what a control volume is, right? What is a control volume? What is a control volume?
The system you analyze.
The system you analyze. Well, if you want to write down the force balance of a bridge, right? You need to cut the bridge out. Not really, right? Just on paper, cut it out. And then you put the forces inside and outside and need to balance. You have some things that are inside the system and everything else is outside the system. And you need to be very clear about what is inside and outside. If you're not clear, you really get confused. I would like to do one example about this control volume. Which one? Why don't we start with this first one? Caesar, I think this was yours. I would like you to comment about what is your control volume, what is inside the model, what you model, and what is outside the model. What is outside the model is called externality. Externality is outside the model. Internality is inside the model. But there's not one right answer, right? You can always have, it's your choice, but maybe before I'll give you another 2 minutes, right, to think. How do you decide what is inside and outside? Ideally, when you model the feedbacks that you're interested in, they should be inside. And if you have forcing or variables that are not affected by your system dynamics, they should be outside. For example, the global oil price, oil on the global market, is an externality. It will not be affected by the problems we have here. right? There's no point for you to model the global oil price if you have these problems. And the oil price will be important for the energy, you know, when you have an energy problem here. Okay? And some things will be definitely internalities. For example, the quantity of the sand extracted from the riverbed. You have a variable for that, and your unit is cubic meters or tons. And that's inside. Something's outside, some inside. And to do this is an art. It's difficult. You need to be creative. And you know, what is inside, what is outside, right? What you want to model is inside, what you has no effect, where you can disconnect the feedbacks outside, ideally. But there is not one right answer, but there is one answer now.
Well.
Blood pollution in the Amazon. What is inside, what is outside?
I think that maybe inside would be the education. I don't know about how people should treat their garbage. And outside, I can't thinking about. I don't know. Outside, I can't thinking.
Outside can be in terms of space. So this is place, this is here, Sao Carlos is outside the Amazon region, right?
Mm-hmm.
It's outside. But also in terms of the processes, you can think of the Amazon region, where you capture some, represent some of the processes, but other processes you do not. You're not interested in car manufacturing in the region if it doesn't affect, right? There are lots of processes that are not in the model. The model is a simplified representation of part of the reality. It's simpler, and it's not the entire reality, it's only part of it. Sorry. A model is a simplified representation of part of the reality. We do not represent every detail because it's not possible, and we don't represent the entire world. Some parts of the world we leave out because in space it's outside of our region either, or because these are processes that are in the region, all right, but we are not interested in, we think it's not relevant for our problem. Okay, this is our guidance of how to decide what's inside and outside.
Inside could be the education, yes. And outside could be the economy of the commerce region there, because we have problems about flood there, but it's not because of the river. It's because of pollution in general, not about this case that I told you. Is because some point of the year the river is full, and the city is the same level of the river. So when the river it grows, it invades the city, but some parts of the city, the flood is because of trash, of litter, not because of the river.
Okay, very good. One example, what is inside and what is outside. Okay, I will not repeat it for all of them. Specify the study period. This is particular for those where we have like a historic narrative. This afternoon I will present an example of a PhD that I supervised about the ancient Mayas in Central America. So this period is between 700 and 900 after Christ, for example. So this could be, for example, the past 100 years or past 50 years, or maybe the future, right? Specify the purpose of the modeling. So why are you doing that? Okay. Felipe, where's Felipe? My question to you is, why would you build this socio-hydrological model? Why are you interested in setting up this kind of model?
Okay, so the purpose. Basically, I want to try to understand if in the future there will be any collapse in such system. I mean, if there will be water enough for the city, for the people that this reservoir is supplying or not? That's my purpose.
Okay. Thank you very much. Can you make the image a little smaller so we can also see the right-hand side? Yeah. So still a little smaller, so we can see the. Yeah, this is very good. So in the first step, the left column was about the hydrological model, and the middle column was about the socio-hydrological model, the control volume. Right, we need a little bigger. Choose the control volume by considering what processes are internalized and what is external. Phenomena are typically even more complex in sociological processes than for hydrological problems, of course. Okay, first step. You okay with that? First step. Now we move on to the second step. The perceptual model. So perceptual model can be bottom-up or top-down. Bottom-up, if I represent individual components. And then I combine the individual components in a way I think is appropriate, then you get the system outcome. That's bottom-up. Top-down is the opposite. I start from the entire system's response. In bottom-up or top-down, guided by observed patterns of the environmental data. The second column is coupled hydrological environmental models. And the right column is socio-hydrological models, so we need to go further to the right. Socio-hydrological models and how we have a conceptual model. A conceptual model is how we think the mechanics of the processes work. One thing leads to another. Now, what leads to the other thing? Now, this is not easy, and we'll make an exercise of that now, and it will take us probably at least 50 minutes for one example. We start usually with a causal loop diagram. A causal loop diagram, we need to think what are the entities, the components of the system, and then we say what component affects what other component in what way. Okay, let's start with very simple problem, right? Classroom problem. We have now two entities, which is the students and which is me, the teacher, with a two-body problem. So we write down a causal loop diagram, which only consists of two entities. Well, Mario and Susanna are also here, so you are the teachers, so you are a separate entity, okay? With three-body problem. So a causal loop diagram would look like that. Students, that's myself, Günter, and that's Mario. And I'm not sure whether I spell your name right, Suzanne. Z or S? One double E. Sanna. So our classroom system consists of three entities. I treat all of you as one entity. And they say, no, we should not. That is not appropriate. You're very different from your neighbor. Of course you are. But then this is where the modeling intuition comes in. What is better, for my purpose, in my context? Represent each student individually, or lump the students together, lump Susanne and Mario together, and myself together. What is better? Well, it depends, right? I'm now sort of strongly suggesting this is the way to do it. You always need to lump. In a talk about scale, one of my professional interests is scale issues in hydrology, apart from socio-hydrology. So then I give an example about scale issues and floods. If you look at a big flood consists of 10 to the power of 18, 1/8. That is 1 and 0 and 18 zeros, raindrops. Are you serious in representing each raindrop individually? No, you cannot. Far from it, right? So you need to lump. The same with socio-hydrological problem. You need to lump. So, and then the question is at what scale to lump? That's our decision, right? You need intuition, creativity to do that. And you could also say, maybe let's split the group in 2 segments. You could do that. Civil and environmental engineers, because you have a different background and they also interact, so that's appropriate to do. Or we lump them. That's up to you. We can decide how to structure that, but it should be in a clever way. Okay? So that's a causal loop diagram. We start with the different entities. It's a difficult decision. And then we draw what we think is the causality. Who affects whom? Have your behavior, does this affect my behavior? Does my behavior affect your behavior? Does your behavior affect that of Suzanne and Mario or not, and vice versa? And what about Mario and Suzanne and myself? Where are the important interactions? Or everybody's interacting with everybody? What do you think? The easy answer is everybody's interacting with everybody, but it's not the useful answer. There is a philosophy, we're talking about philosophy. There's a philosophical school, environmental philosophy. It's called the Gaia hypothesis. Gaia, have you come across the Gaia hypothesis? Gaia hypothesis. Gaia was a Greek goddess of the nature, and the Gaia hypothesis states, it's in systems context, right? It's system science. Everything is connected to everything, right? And I don't disagree, but it's a pretty useless statement, because if everything is connected to everything, what can you do? It's not useful, right? So I don't like this Gaia hypothesis in particular. It's not useful for an engineer. Useful for us, we need to decide, we need to prioritize. If we set the priority, what connection is more important than other connections. If you want to construct design a bridge, you need to decide what is important and what is not. If a train goes over the bridge, the weight of the train, will that be important about the deflection of the bridge? Very much so, right? What about the velocity of the train? Will it be important? Yes. What about the color of the train? Of course it's not important. But you could say maybe because the engineer who designed the bridge liked red more, and because of that he designed the bridge slightly in a different way. It's nonsense, really. Everything is connected, but then many connections are not relevant. So in the causal loop diagram, we only plot those connections that we deem most relevant for explaining our phenomena, and we drop the others. Okay? Have you ever had a course on paper writing? Did everybody teach you how to write a publication, a paper? Yes or no? There is a course, okay. Not sure what they taught there. I also teach my students my own course on how to write a paper, and there is a presentation on the internet. You can Google for that if you're interested in that. And I'm saying, it's important to decide what to go into the paper, what to write in the paper. But it's just as important to decide what to leave out and not write in the paper. It's not useful. Some students do that. I want to be perfect. So I put everything I can think of into the paper. It becomes a mess. It's a real mess. So just as important to decide what goes into the paper, you need to decide what does not go into the paper, and you leave it out. For some people, it's easier to decide. Some people have a hard time deciding in science, but also in daily life. It's not a safe choice to put everything inside. When you talk to your partner, Romeo and Juliet problem, you think, to be on the safe side, I tell my partner everything. Maybe then your partner will be unhappy because you talk all the time. So it's better to decide what to say and what not to say, right? Same here. You need to decide what goes into the causal loop diagram. Now, with this context, 5 minutes ago you said we need 6 arrows. Can we leave out some of the arrows? Can we point out the most important causalities here in the causal loop diagram? What's the most important causality in the causal loop diagram, according to your opinion? The 3-body problem. Please. I'm the teacher. I'm teaching the students. Most important in this context. Okay? Next one. Okay. Yeah. Okay. I think this is also the way I look at it. What about Mario and Suzanne? Okay, what is the effect of Mario and Suzanne on me? Or what's the stronger connection between them and you, or them and me? We have to make a choice, right? Can't have both. Now, in this week, not talking about last year, that's different, but now these 3 days.
Our marks. Our marks.
Our marks. Okay.
Because of the course.
What's more the effect of Mario and Suzanne on you or me? On me?
They can make us speak. They can make us speak sometimes when we don't speak. Mario can look at us.
More effect on you? Okay. Okay, there's not one right and wrong answer, but we're trying to develop the idea, you understand. So, one more arrow. I would like to have 1 or 2 more arrows, but not all arrows. What's the next importance here? You defend your case, yes.
No. I will grade them after the course.
Yes.
So that is one response I need to give to the course and to them. And of course they are waiting for that.
So there's an effect of you on the students, right? We have that. And vice versa, because they also will respond to that. Yes. And then maybe the relationship between Mario, Suzanne, and myself, and vice versa, is not so strong. So we leave it out, okay? So during these 3 days, right? But the point I want to make is, don't put everything inside. It gets too complex. Generally, if you find life is too complex, just outside the classroom, what do? You simplify life. Make it less complex. The strategies for simplifying life. Okay, same here. Okay, so this is the causal loop diagram for our 3-body problem. Let's see what the table says here. Causal loop diagram assisted by the narratives of the phenomena. We now need to build another causal loop diagram for the sociological problem to visualize alternative hypotheses, decision whether phenomena are represented explicitly or to emerge from the system dynamics, right? So is it allow for change in the values if appropriate, possibly allow for the role of social preferential flow and randomness in human decisions. Wow, now there is a lot of words I need to explain. Values, what is a value? What does a value mean here? I'm sure this Portuguese word is exactly the same, but what does it mean? Value in this context, in the sociological context. What is a value? Do you hold any values as a person? I'm sure you do. I'm sure you do. Right. How could you define a value?
It would be importance you give to something.
What you think is important. So the way I look at these things is values are important in politics, just society in general. What you think is important, what you think is not important. 50 years ago, all of the world, people have been training rivers. You know what river training is? Like making a straight river, putting concrete in the river for flood protection. All over the world, the engineers have been doing that. Bad engineers, right? No, they were very good engineers. They did what the society expected them to do. Please train the river so we do not get we reduce the flood damage. They were good engineers. But the value of the society was flood protection is important, nature conservation, ecology is not important. Now, 50 years later, it's the opposite. So the same engineers that restoring the rivers to make them meander with trees and plants, okay? So the value of the society has changed. Personally, I think the value takes the space of life or thinking that is not covered by science. Okay, let me explain what I mean. We all believe in the mass balance. Do we? Mass balance, mass conservation. What goes into control volume needs to go out, plus minus the change. We all believe in mass balance. And I'm just saying belief, because it's not really belief, because we know it's a fact, right? So where we know there is fact, there is no value, because we all agree. We agree on the framework of mathematics and mechanics. We all can agree on that. There's no value. But there is some parts of life where it's not enough empirical or theoretical evidence for everybody to agree. Okay? Do you vote for a Labour government or for a conservative government? I don't want a discussion here now. But some people vote for Labour, others vote for conservatives for very good reasons, both of them. And one group is not more stupid than the other. You may think one is more stupid, but they're all clever people and they want to lead a good life. There's no consensus about empirical or theoretical evidence for what party you should vote. So everybody has their own value through your family and your environment, and no consensus. That's value. Okay, value on so the environment is important, or political preferences. Value could also be explained by preferences. What are your preferences? Would you like to make money, or would you like to have a nice environment? What is more important to you? You can't have both, right? That's value. Okay, so where were we? Allow for change in the values if appropriate. So often you can see a change in the values in society, particularly in the 20th century, from little environment to a lot of environment. And this is not a coincidence. Why is that not a coincidence? Because there is again a causal loop, like a feedback loop. Usually the economic development precedes the environmental development. So when you see an economy growing, and most of the Western countries have been growing in the 90s, if you look at England, that's the first example is England, right? The technological revolution, 19th century, steam engine, coal mining. So, and they had this Commonwealth, this large country, where they had their people to buy their goods, so they made a big profit. The economics of England increased a lot in the 19th century, but the environment degraded. So you have first economic development, and then followed after that, 50 years or so, people realize, well, they damaged the environment, as simple as that. And you see it's dirty, sky is dirty, rivers are dirty, groundwater is dirty. We need to do something about this. And also, we have the economic means to do something about it. Because if you're poor, if you don't know how to feed your family tomorrow, you would not care about the environment. I would not. I would really care about how feeding my children and polluted the environment, but you can't solve everything, right? But when you can afford it, you have the money, and you have a polluted environment, then you clean it up. England did this at the end of the 19th century, early 20th century. We were the first to invent wastewater treatment plants. They were invented in England for these very reasons. Then second half of the 20th century, most of Europe, America, where we had what we call the Water Framework Directive in Europe, or the Clean Water Act in the US. that the environment was dirty. When I was a child, in the 60s, the rivers in Austria were really dirty and smelly. When my father was a child, the rivers were very clear. You could see the fish in the Austrian streams. So when I was 30 years later, really dirty. Now I have grandchildren, 50 years later, and they go to the stream, they're super clear. So it was clear, dirty, now we all cleaned it up. Next example, China. China is now in the situation where Western Europe, or where Europe was 50 years ago, or where England was 100 years ago. They're not polluting the environment. I spent, as I said, a week in China last week, and in Beijing, the air, it's really dirty. But they're working on it, and I can predict in 30 years from now, they have cleaned it up. So there is the economic growth and a lack of two generations, environmental restoration. There is a word for that. It's called the environmental Kutschment curve. Environmental Kutschment curve. Environmental Kutschment curve. That represents exactly this relationship I was just describing. Okay, so where were we? Values. Social preferential flow. Who has heard about social preferential flow? A society, does it act like a gas? You know what a gas is, lots of molecules, and they interact randomly. And then the entire energy of the gas is just the sum of the momentum of the gas, which is temperature, right? Can be represented as temperature. And societies don't work like that. You have leaders, individual people or groups of people that have a disproportionately larger effect on the group outcome than others, okay? Same in hydrology. You have preferential flow paths. When you have infiltration in the soil, some proportion of the soil will represent, will percolate 90% of the water, and the rest will do nothing. And in the landscape, there's preferential flow, which is called rivers, and the rest of the landscape doesn't convey any water, not much water at this scale, right? So that's called social preferential flow, which is probably not, I'm not sure whether this is actually an official term or whether Steve and I came up with it, but you can relate to that as a hydrologist, I believe. Okay, and randomness in human decisions. That's the causal loop. I think what we should do, I think I will just go through these 7 steps, and then when we're finished, we come back and do 1 or 2 examples in detail. Because if we do examples in detail, it takes much more time. And I would like to see at the end of the 7 steps, maybe before lunch. Okay, choice of state variables. What is a state variable? What is a model parameter? What is a force sink? What is a state variable? Can anybody say what a state variable is? And usually with these kind of models, you write the equations down in state space notation. State space notation. A state variable. Any volunteers? What is a state variable?
It's it's difficult to put in words, but it's the behavior or the results inside the model after the force in the model. What happened inside the model after the inputs, like after the force inputs.
I think it's a nice way of putting it. For example, state variable here would be the temperature of this room. You switch on the air conditioning, then energy is taken outside the room by the air conditioning, so there's a flux outside, and the state decreases. The state variable embodies the memory of the system. In a state space notation, I forget about the history. It's a simplification. I forget about the history. We don't keep track about the temperatures of the room yesterday and 1 hour ago. entire history is lumped into one variable. Don't care whether you switched the air conditioning an hour ago on, an hour ago, or 2 hours ago. I only care about the result that we have now to simplify life. Because if you have to keep track of all the traces, it would be very difficult. Your bank account, how much money you have in your bank account currently, that's a state variable. You no longer care about the transfers in the past months or year. Okay, these were relevant and important, but now, how much money do I have now? That's a state variable. How little money I have now, right? State variable. And then we need to decide what state variables we have. Let's do one short example. Jose's Peruvian example, right? A state variable. What could be a state variable in? Would you like to think about it? Can you give a quick answer? A state variable. You understand my question? Okay. I don't know what it is in Spanish. Can anybody translate state variable? Okay. We can explain. Okay.
Eu acho que a principal ideia tem que, com a mudança do solo, com a umidade que tem na bacia hidrográfica, e para depois o efeito de lá, depois a inundação, principalmente lá.
Okay. Okay. Thank you. A number of possibilities, but one would be the total soil depth in the catchment. How much soil is in the catchment? That's a state variable. And then I do some budgeting, accounting. I add soil evolution, soil development, and erosion. I take out soil. Thank you. Anybody else? A state variable? Yes?
In terms of social hydrology, usually in hydrology, water, soil moisture or something, water level in the river. But in social hydrology, linking to economy. So my question is the gross net product. The gross net product of a national product of GDP of the municipality.
Yes.
It's in an output of the system.
Yes.
But the GDP per capita is a kind of variable that represents what is the level of affordability you have in terms of water systems. So this is a question.
Yes. Okay, this was a bit of a subtle question. And I think I understand very well what you're saying, because it was a bit of a subtle question. Usually when you, in modeling, systems modeling, we have state variables, temperatures, we have fluxes, what goes into the system and out to the system, for balance equations. Most of the equations are balance equations. You have the fluxes, and the fluxes must add up to. And now I think Mario has been asking, in terms of, can a flux be a state variable, right? And now there are two definitions of state variables. In a physical sense, no, because a flux is a flux and a state variable is a state variable. In a modeling sense, you can deal with a flux as if it were a state variable, right? So the GDP, gross domestic product of a country. Let's write down a balance equation for the GDP, which is not strictly true because it's a flux, but conceptually you can think of it, what will increase the GDP and what will decrease the GDP. And then you write down the change in GDP in time is a function of other things. Then you can treat it as if it were a state variable. It looks as if it is a state variable in the modeling context, but physically it's not. Does this answer your question?
Yes, but when you divide per capita, yes. So what is your GDP, yes, or my GDP, that represents perhaps a level of affordability, yes, that we or both have to get the water resources, or to buy them, or to pay for them. So my question is related not the GDP for a nation, but the GDP per capita inside the basin. So you have a river basin with people, with the average GDP per capita is 1. And in the other river basin, the GDP per capita is another level. So we have two different river basins with two different GDP per capita. So in these two cases, comparing them, my question is, can we use the GDP per capita as a way of a proxy of a state variable to the water system be more affordable to the humans or not? That was my question.
Yeah, you can always use GDP as a proxy for anything. That's not a problem. But for a state variable, this is something that represents the internal system dynamics. You would call something a state variable if the GDP changes as a result of something that's happening in the system, and it has an effect on something in the system. This is what you call in a systems context as a state variable. In a physical context, you would not. You would call it a flux. But I think in your context, you would. Very good.
For example, we were talking about the difference of state variables and outputs of the model. For example, the water level of a river, it's an output of a hydrological model, but it also represents the state of the environmental in that moment. So how I define a state variable and an output, what is the difference?
Yes. Thank you for the question. There are different ways of looking at it. So let us assume you have a socio-hydrological model where you represent the levee effect. So the water level affects the flooding and the damage, and then the action of the people, like building levees or dams, reservoir for flood retention, will affect the water levels. Then this could be a state variable. But water level could also be the upstream water level, that the water level of the stream that goes into the community. Then it would be a forcing, an input. Or you could use the water level for something else, which is not inside the model, then it could be an output. So there are different ways of looking at the same thing. Not sure whether this answers your question. Okay, so it could be both. Questions? Choice of state variables. The choice of the variables is more further to the right a little bit. More difficult due to 4 subsystems: natural, infrastructure, reservoirs. So in socio-hydrological model, we can represent how people build reservoirs. As engineers, we are not used to that. We just design the reservoir and then have a look at the effect on whether it can cope with the water supply that is needed or reduce the floods to the degree you want to. But the building of the action of the building of the reservoir, that's not part of hydrological or hydraulic models, but they can be part of socio-hydrological models. Socioeconomics, wealth, population, values, institution, governance. Institutions and governance, now terminology. Anybody come across governance? What is governance? Governance? So this is the word that represents how the water management system is set up. So who decides, what entity decides how the water is distributed? There may be an association, it can be part of a government body, a national, state, or local scale. It can be private enterprise who does the governance. But this governance, how the water system is governed. The rules, it's the legal and cultural setup, because it's not just legal, it's also cultural. Legal is one thing, but whether people do that and what they expect, the norms. So this is the governance system, water governance. How do we distribute the water? That's water governance. It's a management term. And then there's another term that's called institutions. It sounds simple, but it's not. Institution is a technical term in sociology and stands for all the rules, norms, and laws in a system. So why are you listening to me and not sleeping? So one reason is that you're interested in it. But there may be another reason, because you are socialized, you don't want to be impolite, right? So you pretend you're interested, okay? You're socialized. It's a norm. It's a societal norm. That's part of institutions. So in institutions, everything that controls how we behave in a society, which is the constitution, it's the laws, and there's an entire legal framework, but also the cultural framework, entire customs. We are used to do that. We expect to have holidays on Sunday and on Saturday and some vacations off, right? So the entire fabric, both in a legal and in a non-legal way, that shapes how societies behave, that's called institutions. It's a very broad term, okay? So, and I would encourage you when you do the modeling, not only do you account for the legal system, but also for the rest, for the cultural, what people actually do. From a lawyer's perspective, the world is very simple. A lawyer's perspective in law, right? It's like the model and the reality. Law is a model. There's black and white, things are allowed and not allowed, and of course everybody conforms to the law. They cannot even think, well, it's expected. Everybody conforms to the law. That's one layer. But the reality is connected to the law. People sort of, two-way connection. What is the two-way connection between law and how people actually behave? There's a two-way feedback. What is it? Two-way feedback between the law and what people actually do. Can you think of these two-way feedbacks? So where's the effect of people on the law? Upward. What is the effect? How do people shape the law? What's the mechanism?
The laws are created because of the people's behavior. I mean, they create the laws.
Who?
People are the institutions.
The mechanism is such. You elect a government, and the government makes the law. Right? So this is the effect from people on the law. Maybe not a very direct effect, but that's an effect, right? And the other, from the law to the people, the law expected to do certain things and not to do certain things. That's the effect of the law on the people. There's a two-way feedback, right? Okay, where are we? Governance, institutions, values are key state variables for long-term treatment, maybe. Mediating variables that drive others are useful if they have independent dynamics. Okay, that's step number. So now we are at the end of this unit, I think. We can stop here and just continue. So for you to understand, my plan is we finish this, the further 4, 5, 6, 7, which will take us maybe the unit today, or 2/3 of the unit. After lunch, we have another unit. And then I would like to do 1 or 2 examples in more detail. And then there is a final chapter to the publication, what the implications of the models are for management. That's what I would like to do at the very end, right? Another 50 minutes. That's my plan, okay? So enjoy your lunch, and we will reconvene at 1:30. Okay? Also,